My name is Dominic Storey. I come from the SourceFire acquisition that Cisco made last year. And my background is I was originally in nuclear physics and fusion physics research. And I did a lot of SCADA work there and developed a good knowledge of how these industrial systems work. And one thing I can tell you, and I've done a lot of, had a lot of conversations with gas, electricity, power providers, all sorts of industrial networking people. And one thing that we have created for ourselves is this perfect storm. We have created better connectivity, IP-based connectivity. It's cheaper now to take a serial, in a new device to make sure everything is connected by Ethernet rather than serial. And then we combine this connectivity we've developed with nation-state cybersecurity programs, the commercialization of hacking, which I'm sure you've all heard about, and of course, hacktivism, the likes of Anonymous and so on. And we've created this storm, which is really that networks are rife for exploitation in this way. And what networks are we talking about? Well, I talk about the third network. The third network for most people's businesses is the control network. Everyone knows about the server network. Everyone knows about the client network. But most people don't think about the control networks within their business. And that control network may be controlling the data center's environmental systems. It may be controlling the HVAC systems. If you look at these large retailers in the US have recently been hacked, the vector for the infection came through the HVAC systems. So these networks are much more open. They're less regulated. They're normally controlled by facilities rather than by the IT departments and the security people within them. So they're the weakest link for most businesses today. How bad could it get? Well, let's create a scenario for you, and then I'm going to explain how I'm going to demonstrate just what fun you can have doing hacking on a SCADA network. Imagine an employee, he's worked for your organization for 20 years, and for some reason he may feel that he's not getting the attention he deserves, or maybe you had to let him go or something, or his business has been taken out. His job is being taken away. So he decides he's going to take revenge on you. This is the worst scenario most organizations have to deal with. The disgruntled employee, the insider who has inside knowledge of your business. And we're going to look to see what that kind of person could do in a control system, not a regular IT system. Well, think about what control systems control. They can not only control your IT, your air conditioning, they could be controlling your manufacturing plant. If you're a pharmaceutical, think of the situation where you may be producing the contraceptive pill. And then you might have this person who decides that he doesn't think women should have contraception, and he changes some of the settings of the process, and all of a sudden these don't work anymore. And 3 months later, there's an awful lot of unhappy women at doctors. So these are the kind of issues we have to be concerned with. So what could our hacker do? Well, he could stop the system completely. He could halt it. But that's kind of easy to detect and easy to fix. He could go and shut down some of the actuators in the system, the things controlling the processes. That's quite easy to see too. He could alter some set points, and now it gets more interesting. That's a harder thing to necessarily see. He may change the process temperature. Imagine if it's just, automated milk production, and he just raises the temperature past the pasteurization point or below the pasteurization point. Milk goes off very quickly. It would be discovered relatively quickly by the QA department. But if he went to go one step further and change calibration factors, that could be something where you wouldn't detect a change in the system for some time. So all of these things can be more and more difficult to discover. And a real Stuxnet style attack, which I'm sure you're all aware of, would be even harder to detect. I told you I wouldn't be doing too many slides, and I kind of want to show this stuff to you in real time. So let's move over to a live demo. So I'm hoping you can see. That's just going to be fun and hard to drive like this. So let us pull that guy up. Can you see my PowerPoint? I can't see anything on my screen yet. 1 second. do this. I'll mirror this over here on my machine so I can see. Right, how's the mirror button? Show mirroring, yep, that's on. So here we go. I'll tell you what I'm going to do. I'm going to bring that browser back up here and put it over here. And you can't see anything. How wonderful. Right. Let's bring that back up here, hopefully in a different way. Arrangement, that's the one. There we go. Good. Okay. Got that? So I wanted to introduce you to my friend here, the RTU 2000. This is a model of a SCADA environment. It's something I built. I took the knowledge I developed in the Atomic Energy Authority, took the standard protocols, handlers and stacks that I used over there, which is Modbus, very common, very widely used, implemented it in a box, and then I control it with standard Modbus software. So this is doing exactly what most systems would do in real world. I don't know if the camera can zoom in on this or not, but if not, then I'll show you what a closed loop system is. A closed loop control system is where we want to control a process, and we have a sensor built into the front here, and it's going to detect a change in temperature, and when the temperature changes, and the temperature should go up in a moment. Let's see if I can get that to work. No, it's because it's decided not to work for me. Give me a moment. See where I do my little tap dance as the machine reboots. But what you're going to see is the temperature as I touch the unit will actually start to rise, and then it will cause this little fan to go on. Now, in all control systems, you will tend to have indicators that the system is running correctly, which is the green light. Then you will have an indicator when the system is slightly out of its operational parameter, which is going to be this orange light. And when all hell breaks loose and it goes really wrong, that's where we're going to have the red light. Okay, so as soon as it's back up, you should now see a reading temperature. Put my hand in front, temperature goes on, fan goes on, and I can also set point to bring it off, for example. Fan goes off. Hand in front, hand goes on, hand goes off. Okay, fair enough. Temperature rises above a certain point, above 60 degrees, then we'll start getting alarms. Okay, so bless him, his Hungarian isn't so good, but it's a bit better than mine. Okay, so we'll live with that. And then, of course, you saw on this that you know, it's a real-time system. If I put my hand in front, the temperature will rise, the needle will move over, and I'll come back down again. Okay, that's normal. Also, these systems have safety interlocks. Imagine if you have a large cooling fan. This is a small model, but a big, large cooling fan, and you need to do maintenance on the cooling fan. You don't want to be going in there when it has the opportunity of turning on. So we normally have the ability to turn that off. And then you'll see an interlock light will illuminate. I would normally get some kind of alarm through my system. I've turned the alarm noise off. Put an alarm like that to tell me that I've got an event, such as these urgent ones here. So turn that back on again. And now the fan comes back on again because the system's running. Now let me clear these alarms off. That's it, clear all in view. Yep. Okay, so all I've shown you is normal process control. Let's introduce our very unpleasant chappy here, okay? He's old school. So he likes his green screen, okay? So he's going to hack into the system. So we can tell he's a hacker. See? Thought you'd like that. Anyway, so what he's going to do is he's going to bypass the standard control systems, access the device directly. And because most SCADA systems do not have any kind of real authentication around these protocols, because they were designed for a time when people didn't think you'd ever connect them to the internet, he can go directly in. So he can, for example, use utilities like a Modbus peek and poke, and then he can read things out of the device. He can read a register value, tell it what he wants to read. He wants to read it as a bit, and see what its value is. Its value is 0. Put my hand in front of it, repeat the same command. Where are we? Is that working? And then let's do that again when it's back on. It's a 1. So we've seen that the device can change and report in real time different values. If I run it again now, it'll read a 0 again. Now, how would he know what values are what in such a system? Well, he's got access to the internal data, so he can do things like this. And let me do that again. Temperature. Spell correctly. He can see what particular registers do what. Now, in this particular case, we've got the actuators which control the fan coming on and off, the control systems, the individual lights, or there are also offsets and multipliers. So, for example, he can also read the actual temperature. So he might decide to say he wants to read, he looks up register 30,000, reads it as a float, and that's reading pretty much the same result on here. Okay, 40 degrees, 40.9, 40.1, what's a 0.1 between friends? And so he can read this data out. These devices, most SCADA devices, also have ways of locking down the calibration factors you make so they're not inadvertently changed. So, for example, on this device, I also have a set point where I can, a write lock, where I can type in exactly what I want to protect. So by putting in a password, a 4-digit password, I will stop this device being changed anymore. Okay? So, put that back on there. So my hacker can also do other things. So he may decide, for example, to look at a register called 40,000. That's showing up here as the temperature offset. So it's a calibration register. Okay? And this is reading minus 60. Now, if I may ask you, sir, if you can tell me what the number says on the front?
So 40.
40, okay. So let's say he decides to change this register to minus 55. Has he changed?
Not yet.
It's reading 46, as far as I can see. So it has changed by 5 degrees. Oh, it won't change here. It's changing physically on the appliance. Sorry, I should have made that clear. Now, if I go to this screen and show what this device is showing you, for example, my graphical view, its temperature has risen. Okay? If I had 2 screens, it would be a quick easier. He may decide to change it a bit more, make it 30, for example. All of a sudden, it's changed to 100 or higher. It's now reading completely different data and sending different signals throughout the system. Let's put that back again. Okay, we'll put that back down there. Okay, so you can see he could create lots of different changes. Now, our guy doesn't want to. Sorry about that. Let me clear these alarms. Temperature has exceeded by more than that degree. So I've cleared that alarm off. If he really wants to hurt my company, he will do things which don't trigger alarms in the system in this way. Would you agree? So he decides what he's going to do. He develops a script. He knows he can use commands to any one of these commands. He has full access to the system to change different settings and configure things. So he develops a script and he runs it. The first thing it does is shut down the interlock, which is stopping the cooler coming on. Second thing he does is he insults people. And the third thing he does is he locks the device by changing the password by using a vulnerability in the box, which means the password cannot be changed back. Okay? It accepts a 4-digit password on this panel, but he used a 5-digit password because the software vendor had left a vulnerability in that it could be changed by 5 digits on the internet. So at this point, as an operator, I hear an alarm's going off, and I look at my screen and I say, yes, 2 urgent events, let's see what they are. Oh, I can see the power state warning has come on. It doesn't have power to the cooler anymore. So when I look at the device itself, back in my graphical view, I can see my interlock light is off. So I will try and remotely turn that interlock back on again, and I will use my watch list actuator, which tells me the same data, but in a simpler way. And I will go and attempt to change this activator back to a 1. So I go and put that back, not that one, so this one, power state, change that back in, and then that should be it. Except it didn't work. It didn't work because the right lock had been locked. And now, the temperature is climbing up to a point where the alarms are beginning to trigger, and I'm beginning to panic. So I need to use a separate system to figure out what's going on. I'll turn that alarm a little bit lower. So what I'm going to do, well, like, you know, that all SCADA people will do is turn off the alarms so they can actually think, okay? So I'll do that one on this one. But what I need to do is log on to maybe a system which will tell me information about what's happened. By the way, once we get to above 80, the reactor will start melting down, so it'll be time to run, okay? So the first thing I can see in the Cisco system, which is telling me what's happening, is I've got a lot of these requests coming in, and it's telling me I've got things like a lock executed. I've got information such as password change made, text-to-speech. These are all very common to what I've just experienced happening. And they've all been aimed at this particular device, 192.168.10.40. All of the others are answers, and so I might quickly look to see what this is. My system will locate information about it and tell me it's been compromised. And I look at the notes, and I can see that this is controlling a radioisotope power generator. Now we're getting to the point where I better do something quickly, or else we're all going to die. Okay? I don't want that to happen today. So, and I look at this event here, it says that this lock happened, okay? Then I want to go and find out what that actually means. So first thing I'm going to do is go and look at the packets themselves. What is the execution lock? If I look, I can find by looking at the what are called rule documentation. It tells me here, sorry, rule comments, meant to click, that this locks the RTU and the password was sent with the previous command to the unit. That's given me enough information already built into the system to go back and look at what the last event said, which is a command buffer write. And within that packet itself, I can see what this password is. And indeed, the rule will tell me it's actually even what offset to look at to find out what this password is. That's actually showing up here. Am I at 100 yet? No, I better quickly do something. So the first thing I want to do, now I understand what that password is. 1, 2, 3, 4, 5. What's the password? I've unlocked it. I can disarm that alarm, re-enable the interlock. Fan is coming on, and I think we're coming back down again. At this point, I've saved my my plant from blowing up. I can even turn the alarms off now that I know what's happening. So What I really did in a very quick demonstration is showed you that we can use information from secondary systems which aren't part of the SCADA environment to give me data about what exactly is happening. Okay? And that data, as you can see, is written in a ways, let me go back to my message view, which gives me very sensible messages, not cryptic messages from an IPS, but messages such as the cooler actuator has been turned on, the calibration offset register has been read. These are rules that, because the Cisco system is an open environment for rule development, we can easily add ones which are configured to instrument this device and give us telemetry and warnings when somebody has done something they shouldn't have done around it. Okay? It's a very powerful way of using security to give you a much better way of controlling your environment. Now, let's quickly switch back, if I can, to the presentation without it crashing on me. So the mitigation that we need to think about, and the kind of things that I've shown, is when we look at a standard Purdue model, which is the SCADA stack, if you like, or IoT stack, we typically have real-time closed-loop control at level 0. Then above that, we then have batch control, commands you're going to send the unit to actually control something, but more like instructions. Above that, we have supervisory access, and these are telemetry historians getting information out of these systems, and so on as we carry on up. These lend themselves to being firewalled effectively, but many organizations don't effectively firewall and contain these zones. And indeed, some of the other things we need to do very well is have good asset visibility. If you've known anyone who has a process control network, they probably don't even know what they have on their own network. They can't scan it because it'll blow up. And so it's hard for them to get real information about these things. So one thing that we can suggest to do is look to have passive asset discovery embedded in your system. So you can find these things out without scanning them. Look for good anomaly detection systems so that if somebody does change something in real time, you will see that actually happen. If you have protocols such as Modbus or DMP3, stuff which doesn't have good authorization built into it, then wrap them with good security systems like the one I've shown you here by using IPS wrappers around them. And then consider that if you can lock down who goes onto these systems, so you can't just plug a PC in and control it, with effective network access control and remediative systems can kick somebody off if you detect something, that's great. But remember also one of the important things is to be able to consider advanced malware issues. And we're going to look at that next. A lovely piece of advanced malware was Stuxnet. Has anyone here not heard of Stuxnet? Okay, I think you were just scratching your ear. You had actually heard of Stuxnet, I'm sure. So Stuxnet was a piece of software written by government agencies somewhere, lest I say that, which actually enabled, by injection into the Iranian nuclear weapons program, destabilized the centrifuges and caused them to shake by actually compromising the firmware in the controllers themselves. And how do we do such a thing? How does Stuxnet kind of work? So what we're going to do is look at the model, once again, the model here, and see how we could do a Stuxnet-style attack. Well, most RTUs and PLC devices will be structured like this. They will typically have an operating system such as a real-time operating system or a Linux component which controls the servers and the services used to command the device, Modbus interface to it, for example, and so on. They'll have an executive which knows how to talk to the real world. But Linux itself isn't really a real-time operating system, so you may have a real-time kernel extension, or you may have a firmware element within the device, such as in Texas Instruments chips, they have a device called PRUs built into their chips themselves, which is a programmable real-time unit. Or in the case of some other devices, you may have separate cards within those devices which are real-time, and you talk to them via I2C or SPI. And that firmware itself then handles the real-time, time-critical elements of the communication. And it's this area that may be easiest to compromise, because it's not necessarily protected in the same way as with complex MD5 hashes and so on, because these devices are very small in terms of their processor capability. So let's go do that. So let's go back to my, hopefully, he disappeared, back to my, my hacker. And my hacker decides he's going to try and upload a piece of software called the malware RTU v2 SPI5 malware, okay? And that is a version of the firmware which has been modified to do a Stuxnet style attack. So all he does, he uses the standard firmware upgrade. So he goes and types in this. He basically says, log on to open the RTU. And he goes in as the admin, which is his normal username to get access to this system. The password was 1234, 4 digits. And he goes to the upload directory. Like this, firmware upload. And now he pushes, oh yeah, passive, PASFIV. He puts his passive mode on because he can't push otherwise. And he puts RTU malware, the Intel hex file, which controls this new code. And he hits send. And the device reboots, loads the new software into the kernel, onto the device, maybe flashing the firmware. It'll come back up again. And it's showing temperature. It seems to be working fine. From my control environment, it looks like everything is fine. So we'll pick up the picture. Where was the picture? There. Everything's fine. But what can you notice which is different? Maybe somebody in the front row could see. Anything notice? Can you notice anything different? What about the fan? What is the fan doing? Turning on, turning off, turning on, turning off, turning on. But it's not in control in the same loop anymore. So now this is the equivalent of what Stuxnet did, which is cause the, it basically caused the actuators in the motors to spin the controller to spin the centrifuges to oscillate, and therefore cause the bearings in the devices eventually to wear out. So by that simple change, I've now compromised the system in a way which may be very hard to detect because everything looks like it's working fine. Except that when I look again in the Cisco system and I ask what I see, hopefully that's coming on. I do a refresh. I think I've got to do that. And that. You'll see that, oh, I know why. I've got to clear that filter off. Let's clear that off. Just for example, we should see it. We'll look over here. You'll see that we have a new event, he said. Let me just open it up so you can see what it'll look like if I went back a couple of hours. Let me show you what the event, for some reason it's not showing right now. Here we go. You would see an event like this. A hex file has been loaded up. We can see what its name is. We even get it shown, and we can take this file and then we can basically click. We can see it was an FTP file, and then we can also say, open this file up. And you know, if you've got a piece of malware, you don't want to just download it and put it on your machine. A, you might run it, and B, it might be stopped by your malware stuff. So what we can do is we basically take all that malware and we automatically compress it, wrap it with a password locked file, and we'll tell you what that is. So I can save that file to my system, and then later on I can then look into that or send it up for analysis into our cloud, for example, put it into a sandbox and see what it does. Okay? So that would give me certainly enough information to know that I really do need to do something about that, and whether it be logging onto the device and then actually unlocking this, reinstalling some firmware back to where we were. I've got 3 minutes left, so I won't take you through that process. So we did that. So what mitigation can we utilize against these kind of attacks? Well, it comes down once again to effective detection and remediation, being able to monitor for and see attempts upgrading software or changing software within such an environment is important. So monitor for HTTP uploads or FTP uploads, whatever. And then I can do that with either snort rules or by using the file systems, file detection system within the Cisco IPS in this case. But other tools you could use to do a similar thing. Deploying advanced malware prevention technologies is important, because if you think about how a Stuxnet attack got in originally, it was via Windows. A Windows share as a USB stick just left lying around by an agent, which then enabled that to finally find its way down into the controllers. So having software that can find this is important. And of course, I think the gentleman before me said about antivirus is looking in the past, is looking to see things which have already happened or that there were rules for. Whereas actually the reality is with any advanced malware, they'll be 0 days anyway. You'll never know they hit you. But what you want is a system that when it discovers can tell you where it is. And one of the things that we have here is the ability that once I've actually got a piece of malware like this showing up, I can go and look even down and finding it. How are we? Sorry. Let's go back. I think we can do this. Sorry, it's not the right one. But what I can do is I can look for its who dropped it, where its path through the environment. And if it's a shard that's come through from maybe 5 different machines, I will see the path through the whole environment. If you want to see these in detail, come to the Cisco stand outside. We'll show you how that actually works. So just to summarize up, because I know I'm within a minute of finishing now. I'd just really like to summarize that all businesses, whether you are in power or industrial, it doesn't matter, you've got a third network. Anyone who's got an access control card they use to get into their building has a control network controlling that, using BACnet probably. You've got air conditioning, and those systems are all linked on a network. And normally they have connected somehow to the internet, because they'd be managed by facilities often outside your organization. So you have a third network, you have to make sure that it's not opening you up to attack when you haven't even considered that possibility. Visibility is paramount. You can't protect what you cannot see. So having a clear understanding of what your assets are, what they're running, and how they're operating is really crucial. And be imaginative in your protection. Just because you buy an IPS or a firewall doesn't mean you can't add new rules or configure new ways of protecting your environment using the investment you've just made. For example, in this case, by having particular kind of rule sets to protect exactly the assets you have. There's expertise out there you can either employ, hire, or buy in. And don't be driven by the SCADA vendor. You know, it's your plant, it's your system. Just because they say, oh, we're not going to allow you to run these things in our network, it's not theirs, it's yours. You know, you're the people who become responsible if you are hacked or compromised in that way. Okay? I think I have finished on time for you. Lovely. Okay, thank you very much. Appreciate that.